Hey, Marisa, what are you reading there?
Hi, Gavin. I'm just reading Kafka's Metamorphosis because I heard that we were learning about metamorphosis today, right?
Yeah, it is a metamorphosis per se, but no one's turning into a cockroach today.
Oh, okay. I'll pick this up at another time then. What are we talking about today?
Good question, Marisa. Today we're talking about rock metamorphosis. A little different than Kafka's.
Yeah, or as we geologists like to call it, by just adding one extra letter, metamorphism.
Oh, it's a little different, I see. Okay, so is that also different than the butterfly kind?
Just a little bit.
Okay, I can't wait to learn all about it. And also for everyone joining us today, my name is Marisa. I work for the Santa Cruz Museum of Natural History and joined as always every week with Gavin and Graham, the Geology Gents. And we are happy to answer your questions throughout this. Gavin and Graham are going to give us a presentation, but also if you have any questions throughout, just leave them in the comments. And also if you have rocks that you'd like identified, you can go to the link in the event description for today and leave them there. We'll be happy to take a look for you. So without further ado, gents, take it away.
All right. So we're coming to we have arrived at our final installment of the Gents Guides to Identifying Rocks. This is part 4. And the topic of this is going to be, as promised, metamorphic rocks.
Graham, I'm excited. Today we've ditched our Holmes and Watson motif, and now we're doing Scooby and Scrappy Doo. So the title of today's Rockin' Pop-Up is "I Would Have Gotten Away with It Too If It Weren't for You Metamorphic Kids."
All right, and so let's dive right into it. We're actually going to skip the whole solving of the mystery, and we'll get right to the end. We've caught our criminal, the gneiss, the spooky gneiss that's been haunting our lab, and it's time to unmask it. And so, Gavin, what's going on with this gneiss? Tell us about all the beautiful things about it.
Well, Graham, this gneiss it's kind of like the rock that we talked about a couple of Rockin' Pop-Ups ago when we talked about metamorphic rocks just briefly, in that it's got that thing called foliation, which is those zebra stripe patterns. And we'll talk about what that means a little later and how we get that. But I see some banding, the black and white banding. I see large crystals. Those bands are separated like in light and dark minerals. And then we have some high pressure minerals, and those are garnets. Those are the chocolate chips in the otherwise nice cookie.
Oh, I love it. Those aren't as delicious as chocolate chips, but they really are quite lovely. Okay, so this is what our gneiss looks like, but it is disguising what this rock originally was. Shall we unmask it?
Yes. What's under the mask, Graham?
Right. The grand reveal. The gneiss was a mudstone. So this always baffles me, Gavin. How are these rocks that look so utterly different coming, how is that gneiss forming out of this mudstone? What are the things we're seeing in this mudstone? It looks almost nothing like the gneiss.
Graham, if you didn't tell me, I wouldn't believe it. This is crazy. It doesn't look anything like the gneiss, as you said. This is a sedimentary rock. It's fine grained. I don't see a garnet in sight. There's no banding, no foliation, no texture. It's really just a nondescript sedimentary rock. So something really, really crazy must have gone on to make this sedimentary rock, this mudstone, into that gneiss.
That's right. So we're going to help everyone here. We're going to take them through how the gneiss got away with it, how it got away with that metamorphism, that just remarkable change, turning from a caterpillar rock into a butterfly rock. And to take us through that, we need to understand the sedimentary and the metamorphic context of how the rock formed. And so, Gavin, why don't you take us through the sedimentary part of this?
Okay. Well, Graham, you mentioned here that metasedimentary problems require sedimentary and metamorphic solutions. And when I think of a place where I can get both of those things, I think of a subduction zone. Because remember what we mentioned a couple of Rockin pop-ups back, in order to get metamorphism, you need heat and pressure. And so in subduction zones, like the one that folks might recognize from the coast of California, you get that. You get a lot of heat and a lot of pressure. And so what a subduction zone is where you have two plates meeting each other, and the denser oceanic plate actually dips below the less dense continental plate. And while it's moving past there, a thing called an accretionary wedge, which you have pointed out here on the left diagram, forms. And that forms when you scrape a bunch of rock and sediment off that downgoing plate, and it forms this little wedge-shaped sediment pile. And so, Graham, what does that have to do with our metasedimentary rocks?
Right. And so that sedimentary location, that's where that accretionary wedge in the shallow regions of that is where we get our mudstones forming. So this is a place where we're getting those things that become mudstones. And then what becomes even more, and then the role that I should say that the wedge plays when we start forming higher metamorphic grade rocks is when that ocean closes. So in this accretionary wedge here, there is some metamorphism going on. If folks caught the green rocks behind us, those green rocks are forming right along the plate part of this subducting plate as the basalt of that ocean crust is being metamorphosed from hot, salty waters flowing through it, making the serpentinite that we've got for our backgrounds today. But then when you actually close up these oceans, right? You feed that oceanic plate down there, and eventually you bring two continents together, like when Pangea formed a few 100 million years ago. You put that mud really, really deep underground, right? You're squeezing the rock together. It gets really, really tall, and you push those mudstones deep underground. And when you push them deep underground, they're both getting squeezed and heated up. That's why I've got that hot sweating face there. And that's when you've got that heat and pressure, the recrystallization of metamorphism occurs. But do these things get hot enough to melt when they're metamorphic rocks, Gavin?
They do not, Graham. And I'm glad that you put this disclaimer here. This is what we have to remember as we go through this Rockin pop-up today, is that metamorphism is recrystallization, but it's not melting. So we're going to say no to melting today.
Great. Well, let's head back to that accretionary wedge and go through the very beginnings of this story. Sound good, Gavin?
That sounds great, Graham.
All right. So we start with the Protolith. And you know me, Gavin, I never miss an opportunity to bring a little Greek or Latin into this. And so Protolith means the before rock from ancient Greek. So what do we mean by a before rock?
Well, so if you were to give me a gneiss, the protolith to that gneiss would be the rock that got metamorphosed to turn into that gneiss. So in our case, we said that was a mudstone. So the protolith is that rock that is forming and is being metamorphosed to which eventually turns into the metamorphic rock. And so you have the protolith here, Graham, and you said this forms in the accretionary wedge. So what's the picture on the left?
That is, so we say, so the protolith has to be a rock. It's the rock that came before the metamorphic rock, but I'm going even a little bit further back, and we're starting in that accretionary wedge, in those deep sea sediments. We are starting with the muds, the very things that make up a mudstone. And so these muds are falling out of the water. They're getting brought in by rivers and submarine landslides, all sorts of wonderful sedimentary process. And these fine-grained muds all collect and get buried. And so as they get buried, they get a little bit warmer. They definitely get squeezed, and that helps them form to a rock. But really, these are quite balmy conditions that the mudstone is forming under.
That's right, Graham. These are sedimentary processes. So everybody who tuned into the Rockin pop-up last week got a lot of those. But for today, we're not going to dwell on them too much. But again, a little bit of heat, maybe a little pressure, but nowhere near the metamorphic heat and pressure we need to start changing these rocks, right, Graham?
That's right. But what do you say we turn up the heat and pressure a little bit?
Oh, let's do it.
All right, down we go.
Okay, Graham. So we're with our thermometer in the center, we're dialing it up a little bit. We got a little bit of heat and pressure here. And so we take that mudstone and we change it to a shale. And so the shale on the right, it's darker, but there's not too many textures that would jump out at me as metamorphic, Graham. What is happening to that mudstone that's making it a shale? It's a little bit of metamorphosis, right?
Yeah, so there's just a little bit of mineral change in there, right? So we've talked about how rocks are all about the minerals that make them up. And so when we go from a mudstone to a shale, there are these little changes that are happening in the mineralogy. They're shifting from the original, detrital, we call them minerals, those sedimentary minerals that are broken down pieces of other rocks. And they're starting to change into things that, like a little bit higher temperatures. They're getting squeezed into positions. The pressure that goes on this rock, we often refer to that as loading. That loading puts some very minor textures into the rock. So if you look here on this shale, there are some sort of flatter features there. You describe the way they break as a little bit blockier or more geometric, and that's absolutely true. A mudstone is kind of crumbly, just like dried mud would be. But once you get to this shale, they tend to have a little bit more of a pattern to the way they break down. So just little subtle changes, but we're no longer a mudstone.
That's right. That's right. And so what happens if we turn the dial up a little bit more, Graham? A little more heat and pressure. Okay. So this looks like something that people might be familiar with, right? This is kind of a household rock, right, Graham?
That's right. A lot of times you can find, slate used to be used for making chalkboards. It's been used for roofing because it's got these nice flat sheets. I'm a big fan of slate being used for cheese boards since I grew up in Wisconsin and love my cheese. Yeah.
I like that, Graham. Yeah, and so Graham, you had mentioned that there's flat surfaces in slate. And so we didn't really see that in shale, right? The shale, while it breaks in blocky geometric patterns more so than the mudstone, has none of that layering fabric. What is that layering fabric, Graham?
Gavin, that fabric is foliation. And foliation is when you start squeezing these things enough that the minerals start to align themselves. It's very hard if you've got a pencil, right, or a ruler. You don't want to, squeeze it the long way, but you can rotate it so that it's lengthwise, and it'll lie, flat like that. So the same things are happening with all these mineral grains. And what does that do for us, Gavin?
Well, it makes it easy to break along sheets. It gives us a fabric that we can identify as metamorphic, right? So when I see this slate, I can see that, and I know it's a foliation, right? The way it breaks, I know it's a mineralogic change, and it's the minerals actually lining up in the rock. So Graham, at the beginning of this Rockin' pop-up, we talked about foliation when it came to the gneiss, which we will get to, and that was those zebra stripes, right? This doesn't look like zebra stripes. So it's not actually the minerals changing and becoming, more pure in one direction or the other. It's just them like mechanically lining up, right?
That's exactly right, Gavin. It's all right now. We're still in the realm of texture. So there are little mineralogic changes, hard to sort of recognize, but what's really important here is they're all realigning themselves. So you've got this nice sort of flat sheeted rock with these slabs, these really, really even slabs inside of there.
Interesting. Okay. So does it go straight to gneiss from here, or is there another step? What happens if we...
Certainly not, Gavin. There is a very beautiful rock that comes between slate and gneiss, and that is schist. And so now we're starting to see things where we're like, oh yeah, this is a metamorphic rock. We're really changing this thing. What sort of things can we see in here, Gavin?
Well, Graham, I see actual different minerals. So we went from mudstone to shale to slate, and while the texture changed, the minerals pretty much stayed to the naked eye pretty similar. But now I see some chocolate chips forming in our cake batter. There are some garnets in there. So remember we said that garnets are a high pressure mineral. So we know that the schist formed at higher pressures, probably higher temperatures. There's also a little bit of a glint to it, Graham. And when I see schist, it's always a dead ringer to me, this glint. It always has this nice sort of shiny texture. And what is that?
Yeah, so that texture that you're getting in there, that shininess, that's coming from that mineralogic change. Here we're getting micas forming. And we've got a little picture of a mica just up next to there. I'll swing my cursor over it. And those micas, they make these shiny flat sheets. Of course, when you're in a metamorphic environment and you're getting squeezed, flat minerals like to form. So those micas are growing out and you've got these nice flat sheets. And those are going to have just a little sparkle to them. And so that's a really good way of recognizing. And that's the sort of the key feature of schists, is that they have these shiny crystal faces that start to grow.
And that's also foliation, right, Graham? It's because they're all facing the same direction, so they all catch the light at the same time. So it's still a mineralogic sort of texture that we're seeing, right?
That's absolutely right, Gavin. All right, and so like you mentioned, we even have some of those key metamorphic minerals. You're not going to start seeing garnets until you start getting to a schist level of metamorphism. You know, schists are going to be forming, or I should say that garnets don't start forming till you get to those heat and pressure conditions that are pretty favorable to making schist. But I think we can still go even hotter, isn't that right?
Let's do it. Turn the dial.
Woo, it's getting warm in here.
We're breaking a sweat here, Graham. Okay, so we finally gotten to the last stop in our, well, maybe the last stop in our metamorphic rock. We've gone from our mudstone all the way up to our gneiss now. So when you dial the heat and pressure up on a schist, it goes to a gneiss. And we can see there's even more garnets. And now we see those zebra stripes. So the foliation is no longer just a textural foliation. It's actually separating the minerals by their composition into distinctive stripes or patterns or layers in this rock, right, Graham?
That's right. And the way we're separating them is, if we think back to our igneous talk, when we talked about those lighter minerals, the felsic minerals, and those darker minerals, the mafic minerals, the mafic minerals are all sort of hanging out together. They're like, ooh, we want to go over here. And then the lighter felsic minerals are like, oh, we'll hang out over here. And so these minerals are sort of preferentially growing into one another, and they grow these thick bands, or, you know, thick to the geologist's eye, to the eye looking at there. You know, these aren't on a microscopic level. These are there for us to see with our own eyes. These, you know, individual felsic and mafic bands that are really showing just how hot this thing is getting, and how it's starting to take on almost more igneous-like behaviors. You know, you're really getting these groupings of minerals separately.
Yeah, and just to add to that and maybe make it a little bit more general for the folks at home who might not remember the igneous talk with felsic and mafic, this is a chemical change. It's chemistry, right? It's no longer changing the rock mechanically. It's actually getting hot enough where you're changing it on the chemical level. Would you agree, Graham?
Absolutely. And so we said we weren't going to melt today, and we're not melting yet. But if we hadn't caught this gneiss and unmasked it for its protolith, and it had gotten even hotter, then we would have gotten to
Migmatite. Okay, so this is a little bit of an enigmatic metamorphic rock because it's not melting, right? We said no to melting, but it's getting hot enough that it behaves kind of like a fluid. It gets kind of mushy, like I like to think of it as a thick caramel where the rock can move in a ductile manner. Ductile is geology jargon for it's moving like a fluid, like a thick fluid. And you get these sort of squiggly stripes. What are those squiggly stripes, Graham?
So this is a migmatite that formed from a gneiss, right? So we're still sort of following our sequence. Each of those stripes is one of those separated bands on the gneiss that this used to be. But then this thing got hot enough that all of a sudden it started getting gooey, and you make these wiggles. And so these stripes are, you know, starting to kind of flow around one another. And that's how we get this wiggly looking migmatite that just looks to me like it was really gooey at one point and kind of flowing around in there.
That's right, Graham. But if we did even more metamorphism, you know, is this the last stop on the heat and pressure train?
It's the last stop on the metamorphic heat and pressure train. But if we turn that heat up even more, we go to another M word, and that is
magma. Okay, so we've taken this full circle now, right? If we took our metamorphism, we got it too hot, it's going to actually melt the rocks. And I like this as an ending point because a couple of weeks ago we talked about igneous rocks. We went to sedimentary rocks. If you metamorphose them, you get to the third, metamorphic rocks. But if you go even further, you go back to the beginning. So this is the full cycle, right, Graham?
That's right. And it's exactly what this is. This is the rock cycle. And so over the last few weeks, we've been able to sort of work our way through all the parts of the rock cycle, showing how you form igneous rocks from a magma. You can break rocks down to form sediments and sedimentary rocks. And then if you heat up any sedimentary or igneous rock, you can make a metamorphic rock. And if you overheat that, it just turns right back into magma and we start it all over again.
Ah, I love it, Graham.
But you know, there's one type of rock that we overlooked just a little bit, or we didn't give it the time it was really due. And that's going to be our focus next week.
As we promised last week when we talked about sedimentary rocks, we'll talk about chemical sedimentary rocks next week. And those are a little bit of a different flavor. You know, it doesn't really fit into each or any of the three categories we talked about. It's its own kind of thing. It's still a sedimentary rock, but we'll get into how that's different and how we can identify those.
Great. I can't wait.
Well, thanks, guys. I think that I have learned a lot from this week's presentation, so much that I would like to take a moment to quiz myself, if you don't mind, because I have just so many rocks around my house all the time. And for instance, I have this rock. And now this rock, I always thought of as like schist is kind of what I assumed it to be. But now that I look at it, it's not very shiny. But it does remind me of like a mudstone that's gone through something. So I'm wondering if maybe this is shale instead, but it doesn't have as many, that foliation that you were talking about.
Yeah, I think you might be onto something there. And of course, this is a rock that has been pretty well weathered on the surface. So I would never tell you to just go around smashing your beloved rocks. But sometimes a fresh surface can be a good way to help ID if it's a rock that you don't mind breaking into a smaller piece. But I agree with you. I think you've got something rather shale-like there. What do you think, Gavin?
Yeah, that's what I was going to say. There's a piece on our right side, your left side, Marisa, sort of near the end that looks like you have a broken side, and it looks to me like I just caught a glimpse of a little bit of a little tiny start of a foliation. So this might be, my guess would be shale. In between maybe shale and slate, there are sort of subcategories. So you might have hit a subcategory, but I would say that you're not so much in a schist. You're probably closer to the lower end there.
Okay, all right. What about this guy right here? So this one, I always thought of as slate, but it is very shiny. I don't know if you guys can really tell that. There, do you see that?
It is pretty shiny. Gavin, would you like to say, speaking of subcategories?
So I would call it, close to a schist. What were you thinking, Graham?
I was thinking that could be, so there's a rock that Gavin and I debated whether or not we talked about it today that falls right in between a slate and a schist, where it's a little bit too shiny from getting mica starting to form to really be a schist, but they're not quite big enough for you to say that these are, macroscopic or, crystals you can see with the naked eye, and that makes it a schist. So what falls right in between slate and schist is phyllite, spelled with a P, of course.
Yeah.
Okay.
Yeah, I think that's a good one, Graham. I think you're right on that.
Okay, that's very interesting to me. Okay. Last one, a very heavy rock. This one I don't think falls aligned with what we've been talking about with the mudstone transformation, but I think it might still be metamorphic. And that's because it looks to me like there's a lot of like crushing that has maybe happened. Do you see like that cross hatching there? So I was thinking that maybe this was something like granite. It's really heavy, and maybe granite that's gone through metamorphism, or something like that. What do you guys think is happening here?
Graham, what do you think those cross hatches are? I can't really make that out.
I know, this is, in a way, it almost, there's like a blockiness to it, and so the igneous side of my brain says this definitely was a granite. The sedimentary side of my brain wonders if maybe that might be a conglomerate with those big rounded chunks in there. But I don't know, Gavin, what are you thinking?
I think that it's probably maybe on the meta-igneous sort of meta-granite side of things. That'd be my guess, but it's kind of hard to say. That's another one that I would have to either have it in my hands or break it to really say. I'm not positive on that end.
Okay. So the other submissions that we have are not from my house. They came in online, and we did get quite a number. I would say dozens from one source. And so I picked out a couple that I'm going to share with you all. And maybe we can just go through a couple of them, see what you think. So the pictures, they're kind of not the best quality. Do you guys see this right here?
Yes, the bright green rock in front of us.
So do you have any sense of that rock?
I think this comes from a skarn. This is the type of thing that you get in the azurite sort of malachite range of things. It might be a sort of more exotic version of that, but I would think that this is like a hydrothermal type of.
Yeah, my guess, just looking at that, you see a little bit of a layering to it, that sort of deep bluish green color. That to me looks like malachite, but it could be, my guess is it's any sort of copper rich hydrothermal mineral.
Yeah, totally.
Okay. All right. What about this one?
This one is definitely desert rose. It's gypsum. And gypsum forms, gypsum is a kind of weird mineral. It can take on many forms. And this is one of the ones that it's really famous for, right, Graham?
That's right. Yeah, these are really pretty natural gemstones that form out of these neat chemical sedimentary rocks, which we'll be able to talk a little bit more about next week.
Yeah, so that's two chemical sedimentary rocks.
Is this one too?
Absolutely.
Okay. I'm wondering, Gavin, do you have anything in particular to say about the grouping of all of these? Maybe this one?
Okay. This looks very familiar to me. Are these my rocks?
Yeah. So, again, we have dozens of these to pick from, but Gavin's mother, Vicky, sent in a lot and requested specifically that we keep it a secret to see if you're able to recognize.
Yeah.
So I'm wondering, Gavin, do you want to talk for a second about what it was like to be a young rock hound?
Of course. So I think that those rocks, the green one was one of my first rocks, and I got it when I was like 5. And so I kind of just liked rocks because they looked cool, and I kind of just got into it more and more and would find some that I liked and go to shows and things. And so I'm not surprised that my mom pulled the trick on us like this, Graham, because, she's at home with all of my rocks now. I didn't take any of them out to California with me, but I have a pretty extensive collection, and it turns out kind of nice because most of them are chemical sedimentary rocks, and that's what I study now. So.
Yeah, that's great. Yeah, I know. I was like, oh my goodness, dozens of rocks. How are we ever going to get through all them?
Graham, do you have any stories about being a young rock hound? Did you collect rocks too?
Oh, when I was wee, I was very taken with just all natural history collections. So rocks, shells, bits of trees, feathers whenever I could find them. So yeah, I think, I found my way into geology. I was never taken with rocks from the very beginning like Gavin was, but I definitely grew up loving natural history, loving being able to collect things, and rocks for me were kind of, once I realized that I could make a career out of collecting rocks, I was pretty sold on that.
Living the dream.
Absolutely.
Well, thanks for sharing your personal stories with us. We did have one question in the comments that I'll throw your way too. Could you just clarify the difference between magma and lava?
Oh, very good. Gavin, I'll let you take that one.
Ah, fantastic. Okay. So magma and lava are both melted rocks. However, magma is when you have a melted rock that stays beneath the surface of the earth. And lava is a melted rock that comes out in or onto the surface of the earth through volcanoes.
Great.
You got anything to add to that, Graham?
No, I'd say you hit the nail on the head.
Covered it.
Well, thanks for clarifying that. And I can't wait to learn a little bit more about some of these rocks that we saw from Gavin's collection next week when we learn about chemical sedimentary rocks. So thanks everyone out there for joining us. Sorry if there were any technical issues with us going in and out, but thanks for sticking with us. And guys, I'll see you next week.
See you then.
All right, see you then.